original scientific program for Andes was discussed in one of the first meetings, and then concerning neutrino physics, we aim at to develop some line along double beta decay, which is my favorite, of course, and then getting, a large Latin American neutrino detector. Could be, an oscillation-inspired experiment, like Borexino, and then focus on low energy, and else, the solar and supernova neutrinos. But then because, the R&D in dark matter experiments are just focusing on what is called the modular expression of the detectors, so we established contact, with some experimental groups who were developing, modulus, and some of these models can be placed in any place. Essentially, we were just looking at the same kind of experiments as the sort of modular Majorana experiment for double beta decay, or modular experiment like Minix for dark matter. But then, there was the proposal of new technologies for those detectors, and then the new branch of geophysics emerges naturally in the place, as well as the pure geological application, because the laboratory will be placed in what is called a flat slab. There are two plates in South America which are moving one against the other, so the laboratory is just on top of one of these plates. And then biology, which is very interesting. Somehow to disentangle between the effects due to radiation and the effects due to say, mutations, which may happen in a large community, say, of bacteria. So the proposal is to grow bacteria at the surface and grow bacteria in the laboratory. The one at the surface will be exposed to radiation. The one in the laboratory will not, at the same degree as the one in the surface. So then we can really make those studies. The evolution of DNA's distortions along generations. And then there is a room for accelerator physics. Like the sort of Laguna kind of experiments. And as we're going to show you later, we already have some proposal for building, this kind of the accelerators in the laboratory. And we also have to do a kind of experiment like the one of Opera there, but at longer distance, because if one is dreaming of a neutrino being running from a big neutrino facility, we are just about to reach the magic distance of 12,000 kilometers for neutrino oscillations. So this is kind of experiments who has been already proposed to be placed in the Andes facility at the level of the modular scale. So one is NEMO, that will be upgraded to Super NEMO, but this is the one that is actually located in Frejus. So one of the modulus will go to Andes. So NEMO is a very dedicated experiment to neutrino double beta decay that is acting really as a detector and not as a passive detector. So NEMO is just measuring tracks of electrons coming from the double beta decay emitter, rather than measuring only the amount of materials which is converted by the decay. So really they can measure tracks from the electrons and measure angular distributions, which is extremely important for the discussion of the mechanism that go beyond the decay. The other is that kind of a large experiment devoted to oscillations, which is one on the other panel, this panel here, kind of Borexino. And then, of course, will be the dark matter experiments like DAMA, where we somehow benefit for the fact that we are in the southern hemisphere, so we are having the seasonal modulations, shifted by half a year respect to the ones that happen in the northern hemisphere. And then nuclear astrophysics, I mean, is a natural line. And then I have been talking about Luna, so we got the proposal from the group in Oak Ridge, and they want to use, I mean, part of their accelerator. So we want there to make this kind of experiments. Okay, now this is just I will take only 1 minute. I mean, as a professional distortion, because this is something which I like very much. Is just the connection between what is something that you call a passive thing, like neutronless double beta decay, with something which is a reaction thing, like LHC, PP collision. So the physics which is in here concerning neutrinos is the same physics which is in here. So the two types of things are really complementary. Therefore, having a facility devoted to double beta decay at the time when the experiments at high energy are flourishing will be really very, very, very nice. So we'll pass very fast. It's not interest in that. And now this is a view of the Agua Negra geology. So all this portion represent, the colors represent the composition of the rock. They have been already taken some samples in the mountains, and based on these samples, the radioactivity of them was evaluated. So, and from there, the composition of the place where the laboratory will be built is mainly composed by andesite, rhyolite, basalt, and these other two rocks. And the water equivalent associated to the place is about that. So there is a possibility to move the laboratory even 100 meters more to the south, where then if we are able to do that, so we can really be second in the world in concerning these values. I mean, second only to SNO. So this is a background estimation. I guess that Hernan Azorey was working on that also. What is mine? Okay. So, and this shows, I mean, the expected, I mean, composition and the radioactivity of the rocks at the place of the laboratory. So here is a simulation of the deep muon flux and neutron activation at the depth of the laboratory. And this is the concept of the laboratory. So there are the two tunnels, and then the auxiliary tunnel, and the caverns, and the pit. The pit is devoted will be devoted, I mean, to the neutrino oscillation experiments, and these two caverns, in principle, to dark matter and double beta decay. And along the gallery here, we want to place, I mean, the accelerators. So the typical size of the laboratory, the main hall will be like this, the order of 20 by 20 by 50 meters. So for all the structures that I'm going to show you, the shape and the volumes have been calculated so to give them, I mean, the largest possible stability. So the total cost of the construction of Andes amounts to less than 2% of the cost of the tunnels. And so this is a figure that one has to keep in mind, because it's very important for political reasons. In the sense, it was very easy somehow to convince the authorities that we are not building there a white elephant that therefore will be impossible to manage at any level. So, of course, if the tunnel is not there, the laboratory will not be there. It's impossible to go to the deep and to the location of the laboratory if you don't have the tunnel. But now that the tunnels are going to be built, it's much easier to think of a laboratory. This is a preliminary view of the laboratory layout, where we have, the different components. There is a change from the previous drawing because that was a concept only, and this is rather a semi-final design for the laboratory, where you have, the caverns and the pit, the connections between them, and the auxiliary rooms for other experiments, and the galleries, and all the aspects which are covering the ventilation of the laboratory, the power needed to run the laboratory, security measurements, and specifications for the walls have been carefully studied. This is a table where the volumes of the main hall and the service hall and the primary and secondary pits and rooms are given. So it will be a very large facility, much larger than Modern. And there is shown, the excavated volume and the final volume after taking the concrete on the walls. Well, this is in some large scale, the disposition of the laboratory, and this is a measurement for the caverns, the lateral tunnels, and small caverns. And the auxiliary tunnel. So to compare with, we have drawn here the size of a truck and a car to indicate, the relative size of the laboratory and the possibility to, to carry, the equipment from one side to another. It has the advantage that because it is not a mine, it will be at surface, so it's much easier to move everything in there, as well as the main hall. Well, so all these points, which I have mentioned before, have been written in the Andes technical report, which is in the page of Andes, and we have already received, the technical evaluation by Tony Noble. Tony Noble is the director of the NO laboratory. So he went through all these points very carefully and was pointing out, to the weakness and strong points of the original design, so to change it accordingly. Now the same documentation was sent to Gran Sasso and to other laboratories, and we are just on the way of collecting the information to finalize this stage of defining the parameters of the laboratory. The Andes surroundings. So we are planning to build 2 stations at each ends of the tunnel, one in Chile and one in Argentina. And of course, there will be some areas for supporting laboratories, essentially in La Serena, in Chile, and in Rodeo, in San Juan. So this because the proximity to the harbor, probably all the equipment will go by sea and will be somehow pre-built in La Serena and then transported to the laboratory place, which is in here. And the same from the Argentinian side. And of course, since we're in a region where both in Argentina, say from Argentina and Chile, there are universities and places where we can eventually develop, activities related to the laboratory. The next step was to think of institutes related to Andes, And we already got, the confirmation for one of these institutes from the Argentinian side. So how is the status of Andes? Well, we got already some 20 or more letters of international, coming from international laboratories giving support to the initiative. We got more than, now these numbers are obsolete, more than 30 letters coming from Latin American groups. There were already some workshops in Argentina and in Mexico and Rio and in Chile. So the proposal went through all the quality assessment and evaluations, both scientifically and from a technical point of view, from the Argentinian Ministry of Science. There is a commission which is called the Commission for Large Facilities, and we went through it. We were competing with some other projects, and we got the first place in that evaluation. And then we also got the official support from the EVITAN. EVITAN is are the Spanish acronym for a binational entity for the tunnel. So this is a organization composed by members of the parliament from Chile and Argentina. And because, the management of the tunnel was approved by law for the two countries, and therefore this ente is the one who is going to administrate, and to follow up, the advances on the construction of the tunnel. So what about the formal aspect of the organization of Andes? So the Center for Physics in Latin America, the CLAF, has already created an Andes unit. So this happened this year in January this year. So now there is an Andes unit working under the umbrella of this Latin American Center for Physics. And this is the first step towards the consolidation of the consortium that will run the laboratory. So as I said before, there was an international call issued in June 2013, and the process was continued in 2014, and then it finalized already last September. So the Andes design, the design of the laboratory, was already confronted with the design of the tunnels. So it was a joint work with the Lombardi company. Lombardi company is a company who will be actually in charge of constructing the tunnel. So Lombardi is the same company who was working in CERN and in the underwater channel between England and France. So we are, in this respect, pretty sure that they have the right technology to work. There was already, this study was already approved by the other minister, not the Minister of Science, but the Minister of Planification, which is the one in charge of the public work. So the conceptual study will be presented by the end of this year. As I told you, we are receiving now the opinions from the experts coming from the other laboratories, underground laboratories, to finalize the design. So the details, fine details of the engineering of the lab will be coming by the middle of next year. So this is a very delicate question here, because we have to talk not only about the composition of the concrete needed to finalize the walls of the laboratory, but also the pumping of air, because the laboratory has to renew the air every 1 hour or so, just to remove the radon that may be coming in, and also the air will be taken from outside, so the radon will not go in, because there will be a stainless steel pipe of 5 kilometers long running from the laboratory to the end of the tunnel to take the air from there. We cannot dig in, to the top of the mountain. We can take the air from the surface. And also security, in the sense that the laboratory will also be working under high pressure to prevent, fire hazards coming from the traffic tunnel, in a sense. And there will be also, it's second and third barriers to prevent any hazard coming from outside to the laboratory. So Andes will be included as an additional to the civil work on the tunnel. We got a written confirmation by the governor of the San Juan province. That was 2 weeks ago that Andes, in fact, will be included in this item. Now we are working in the final evaluation of the environmental risk, which is needed, to incorporate, the laboratory, to integrate the laboratory to the tunnel. So this study is actually going on. So what is next? Okay, then we are preparing for a conference in San Juan, which is the place of the laboratory next year, where the official announcement of Andes construction will be made. And then we are just developing plans for a regional experiment, a kind of flag experiment that most likely will be along the neutrino oscillation lines. And of course, we have to establish connections with other laboratories like Gran Sasso and Snow Lab. They're already going on, and then the agenda will be open for running and planning experiments. And then there will be this post-graduation and midterm schools and seminars and workshops for students and young researchers. So what about the consortium? Well, we have to accommodate the Andes initiative, the construction of the underground laboratory in the frame of the Mercosur, on the UNASUR. So we did already went through all the bureaucratic steps to, just to solve all technical problems, like, running of an international laboratory under the limitation that each country has. So one has to remember that perhaps the only or the unique experience in the successful large-scale experiment is Auger. There are no much experience in Latin America about this type of enterprises. So, but Auger is an experiment. It's not a facility yet, and it is located in Argentina, and its aim from the beginning was aimed as a place for an international collaboration. While here we are just aiming at an international laboratory. And as you can imagine, there are several laws, which make regulations on this aspect, and we have to be careful not to think of aspect against those regulations. So, and in this respect, I guess the example of the CERN is perhaps, the most illustrative. So we are really copying the structure in the sense that this will be a consortium where the countries are just being represented in the way they agree and the way they choose, where the managing and the financing and the funding of the laboratory is being taken by all the countries which are members of the collaboration, or in this case, member of this CLES agreement, and where the research lines are not restricted, say, to physics, but also to the other very promising lines in technology, in geology, and in biology. So the CLES has as main purpose to just to run the laboratory and manage the cooperation among the countries which are members of the collaboration. Initially, the countries are Argentina, Brazil, Chile, and Mexico, but we are not excluding any country in the region. So we want to encompass then this large structure and integrate, not only the purely scientific aspect of the project, but also the academic one. So we aim at, like in Gran Sasso, having a kind of institute where the physics and the science in general of the experiments which are conducted in the laboratory are developed. And so in this respect, the CLES will not be a purely bureaucratic organization. Like in the CERN, like in the case of CERN, it will aim at making the scientific agenda and all and monitoring all the related activities of the laboratory. So Andes will be a motor for regional integration, no doubt. And then in the CLES agenda is the definition of the Andes organization, and then the identification of the regular financial sources for running the laboratory, and of course designing the long-range plan for the laboratory. So then the conclusions and prospects. So we think that the construction of the first underground laboratory in the southern hemisphere opens a unique opportunity for Latin America, and in particular for the international community, to have, an international facility that at the beginning will not have the limitations that the existing facilities have. I mean about the volume needed to allocate the construction of second and third generations of the current experiment. So if I extrapolate the volume, say, of SuperNemo or Borexino or this kind of experiments, or else if I think of things like Cuore, cryogenic facilities, or accelerator facilities like Luna, then this laboratory will be able to accommodate, for at least 2 more generations of laboratories, not to mention new openings and new designs of the experiments. Then the second point is that if you think of that region is very close within the range of Oye. And then you cross the mountain, the Andes, and from the other side you have La Serena, and you have the European laboratory. So it will be a fantastic place to study neutrino physics, because you can have any potential signals coming, say, from supernova or extragalactic objects. They will be immediately detected both from the neutrino sides and from the astronomical sides, and therefore will not happen like it happened with the 1987 supernova explosion, that the neutrinos unfortunately were not detected as a rate we needed. So it will be really main complex for the activity, and then of course concerning the project itself. We think that we have in the region enough critical mass and facilities to be really at the frontier of the research. So then the by side result of the initiative is will be also the growing up of the community. So we are thinking of the place as a place to somehow to motivate young generations. It's not a laboratory. The horizon of this laboratory is not, a couple of years. So we are talking about I don't know, 20, 30 more years to develop, the full structure. So it will be really very, very nice opportunity for the region. So I would like to finish by asking all of you who have interest in joining us, to think of writing proposals, for the kind of experiment you would like to perform there, or even to join us in the activities which are related to the white paper of the laboratory concerning, the kind of science that we want to develop in the laboratory. So the main chapters we have are, of course, neutrino double beta decay, dark matter, neutrino physics, and then the interface with high energy physics by the connection between the observables from both fields. And the other aspect of the white paper are just dealing with technical questions like growing materials under conditions of low radiation, and doing biology also under conditions of low radiation, and seismology. So please, feel free, and we're going to be very happy to receive your proposals. So this is the web address, and my email address was given at the beginning of the talk. And so we really hope you will take this initiative as something that perhaps can help to change in a very dramatic way the face of the region. So thank you very much.
Thank you, Osvaldo. We have time for questions.
Well, it's just a naive curiosity. I've seen that the hole have a length which is about 3 times the width. So the question is if...
you mean the size of the...
Yeah, the size. I remember 40 meters and 15 meters large.
This one?
Yeah, these numbers.
Yes.
So the question is if any specific orientation has been chosen, or if just is...
Yes, so the size of all the caverns and so have been designed so to ensure stability, kind of domo type, so to prevent, essentially the ceiling of the structure to become unstable. And then the other is that for the pit, for instance, the size of the pit, it will be a very huge pit. So then the access to the pit will be from the top, not from the bottom, of course. And there you have to put there, some mobile platform to reach all the places. So we calculate already, all these limitations in concerning, the weight of the equipments and the size of the tracks, and so that will move in there. So in this respect, Lombardy is, because if you're going to build this facility, you will say, okay, I want the largest possible room. But then those guys who are the ones who are building the tunneling machines are telling you, which are the real limitations. So these machines are, they're kind of, they're eating the rock and practically making at the end, the wall of rock will look like a finished one. But they're advancing at this rate. So they're not easy to move, the machines in any direction to dig in. So for the caverns and so, most likely they are going to use, a conventional blasting methods, explosive, okay? And then making the hole, removing the materials, and then finishing the things by hand. And this is the real limitation for the thing. So the geometry is somehow dependent on the structure of the rocks, so that the tensions that you are creating in that place are compensated in a proper way.
Ernesto, la última fila, atrás.
Osvaldo, we know that the tunnel, the project of the tunnel is already done. So my question to you is, what is the difficulty that you foreseen to include the modifications in the original project from the side of the engineering company? Because everybody knows that when you have a project that is already approved, to do minimal changes is very, very complicated. Could you please comment this for me, please?
Oh, yes, I mean, so the cost of the, say, further design,
I'm not talking about cost. I'm talking about
practical
practice.
change. Okay,
yes, to these modifications to be approved by the civil engineering company, because the project for the tunnel is already done.
yeah, but this is because, I mean, when Javier went to Geneva, he went there with to discuss with the Lombardi people. So the Lombardi people will build both the laboratory and the tunnel. It's the same company. So, I mean, they knew already, they have, I mean, somehow a margin for changes, if you want. So our purpose is that we don't want to face unexpected difficulties coming from the construction of the tunnel that may reflect upon the design of the laboratory. Or else that going to the laboratory, I don't know, local conditions that may force any change in the design. We want to be flexible enough so that if the changes happen, they will be absorbed in the construction of the laboratory. I don't know if this answers your question. So we are flexible enough. These are somehow the minimal conditions required for the laboratory. And the Lombardi company already agree somehow in this respect. So say the laboratory parameters that we are working with now are the ones who have been already somehow approved by the company that will construct the tunnel. They will not be two different companies, it will be the same company.
Okay, so they already made some kind of revision on the project to include the construction of the
I told you,
tunnels.
I mean, Bertu went to Lombardi headquarters with the project, and they make the review of the project, and they gave the okay. But then to make sure that we are not missing any significant point, we send this document to, say, Tony Noble and to Juan and to the people in Gran Sason company, so to get, I mean, some extra opinions on that. So to make sure that we are not missing any critical point. And the review of Tony Noble was extremely useful because he was the one pointing out to some changes in the design, particularly the access to the laboratory. So he was the one who was proposing the construction of an extra gate, an extra gate in here, because these points will be somehow the isolation points. You see, it was not in the original design, but he was proposing to build now two gates instead of only one gate to separate, I mean, the tunnel from the laboratory. And then the other thing about the access to the pit and to the main cavern was also changed respect to the original design, who was this one here. You see now these connections have been suppressed. Now we have a larger gallery here and two extra pits in there. And then two more gates to isolate the laboratory from the tunnel. So if you compare this design with that one here, it looks very different. But still, different in the design, not in the concept, and then the minimum size of the pits and the caverns are already in the proportion we wanted to be included in the project.
Okay, let's have one last question.
So what's the level of seismic activity?
Excuse me?
What's the level of seismic activity?
Well, I can show you the, if I found it. There. So this is a simulation. Yeah, this is radioactivity.
No, seismic.
Safety. Oh, seismic activity. Well, I mean, so the San Juan region is not, as well as the mountains is not a very stable one. I mean, they happen earthquake from time to time. But in that location, as I said, there is a huge, huge flat plate. So that means if something happens, the laboratory will move as a whole. And therefore, the risk of having a breakup in the middle of the gallery or so is somehow very small, at least from the from the statistics and the projections of the seismic activity in the region. So the last somehow main earthquake in San Juan happened in 40 years ago, but happened much in the south of San Juan, not in that place. So we are pretty sure that the place is somehow safe in this respect.
All right. So let's thank Osvaldo again. And before we break up for lunch, we have an announcement.
We have two announcements. The first one is about the certificates of attendance, and they are ready to be downloaded from the webpage of the event. And the second announcement comes here. Here it is. Extraíble. Tú lo puedes poner. Okay. So, my colleague Juan Pablo Beltrán, who is here, Cesar Valenzuela Toledo, and me, Jason Rodriguez, are organizing the first workshop on current challenges in cosmology, inflation and the origin of CMB anomalies. This workshop will be held in Cali next year in March. So the other organizer is Juan Carlos Bueno Sanchez, who is our tripartite postdoc. So we have a preliminary list of speakers. We can see people like Vyacheslav Mukhanov, David Light, Jean-Philippe Poussin, Jiro Soda, etc. So the idea is to have at least, at most, 3 talks per day, and plenty of time to discuss the topics. The topics of this workshop are statistical anisotropy and anisotropic expansion, anisotropic non-Gaussianity, primordial magnetic fields, CMB data analysis, parity violation and polarization in the CMB, primordial gravitational waves, effective field theory of inflation, and Galileo's and Hordesky theories. So if you want to attend, then of course you are welcome. Thank you very much.
Antimatter and dark matter searches in space.
Okay. Hello. First, I would like to thank the organizing committee because the invitation to come here was really a pleasure, and also to congratulate them because the organization was very, very good. Thank you very much. So then, let's go to the talk. As has been already introduced during the sessions this week, the weakly interacting particles are good dark matter candidates, and there are 3 independent methods to search for these particles. One is the direct search made in underground experiments using the scattering of the dark matter particle with the ordinary matter, and this was already very well summarized. Was well summarized by Jose Matias Tuesday. So another possibility is to produce these particles with high energy accelerators, like in LHC. Another way is to look for the annihilation of the dark matter particles in cosmic rays by looking excess of particles like positrons, antiprotons, electrons that could be in excess of the ordinary background that we expect from the cosmic rays. Before going, that should be the matter of the talk. Before going to that one, I would like to make a little introduction to cosmic rays because it's going to be the standard field where we are going to work for these things. So cosmic rays are samples of solar, galactic, and extragalactic matter, which include all known nuclei and isotopes, as well as electrons, antiprotons, and positrons. The flux runs for more than 31 orders of magnitude and is quite well characterized by a power law with a spectral index of 2.7. The main components of the cosmic rays are protons and helium, 90%, 10% more or less. And here I saw the flux multiply, scale it by the energy to 2 to the 7 to see better the structures. At least till 10 to the 6 GeV, cosmic rays are assumed to be produced in the are assumed to be galactic origin, and supernova Riemann expansion are very good candidates for providing the acceleration that the cosmic rays provide. So here is a summary of the experiments that they have been taking data for a low energy. We call low energy from the knee, below the knee. Most of them have been balloon experiments. For high energy, as this morning Esteban was already summarizing, we need much large detector because the flux is very low, and it's not possible to have a small detector to detect these low fluxes. The composition and the energy spectra of the nuclei are typically interpreted in the frame of the context of propagation models. Once the particles are accelerated, they are injected in the interstellar medium, and they are coupled to the medium through the magnetic field of the galaxy, the magnetic field of the galaxy. So in the process of the propagation of the particles, they suffer of diffusion due to interaction with random magnetic fields. They suffer about reacceleration and also convention transport outside the disk. And also they suffer some energy losses with interaction with the interstellar medium. And some particles are destroyed and some particles are produced by spallation. In this context, particles like proton, helium, carbon, oxygen, nitrogen are considered as primary, and they are supposed to bring already the information about the source of the particles. While particles like deuterium, helium-3, lithium, beryllium are considered as secondary, and the information of the energy flux that we see in the secondaries with respect to the primaries give us information about the medium where the particles have been moving through. To understand, therefore, the origin, the acceleration, and the propagation of the cosmic rays require the knowledge of the chemical composition over a wide energy range. It's a summary from the PDG, Particle Data Group, of the direct measurement of the fluxes for several nuclei, protons, helium, carbon, so on. These measurements were, as I say, mainly made by experiments on balloon. They suffer from the short time of exposure time, and also they have a limit of the atmosphere. Even if the balloon can fly quite high, they have some kind of background. Also, the statistic is not very good. So in that sense, mainly due to statistical limitations, it's not possible to make some studies about cosmic ray propagations that should be interesting about to see the differences in the spectral index of the different elements. About the secondaries, this is a plot of the boron to carbon ratio, the energy spectrum, the boron to carbon ratio that runs till 100 GeV, also made with balloon experiments. And as you see, this ratio is a key measurement for the understanding the propagation, the density of the material that the cosmic rays are traversing. And the errors are quite huge, and the statistic is limited. And also there is a level of the atmospheric production where you already cannot reach. You have already too much background. About electrons and positrons in cosmic ray, they are rare case. They are less than 1%. And the known source for positrons is collision of standard cosmic ray particles in the interstellar medium. First measurement of the positron fraction, that is the fraction of positrons over electrons plus positrons, was made in 1964. But the first measurement of the spectrum was in 1969, and was looking at the shape of the spectrum from the point of view of getting information about the propagation models. Later on, some years later, measurements from HEAT and the TS93 provide kind of disagreement between the positron fraction that they measure compared with the expectation. And this disagreement at the level of a few sigmas was considered possible source of anomalies due to pulsars or perhaps exotics, and already originated a lot of interest in the field for both astroparticle physics and particle physics field, because pulsars and dark matter may produce additional positrons and antiprotons. And in fact, depending on the kinematics of the mass of the particle, the shape of the enhancement that you can expect is different. So there was a lot of interest in this kind of measurement. But as I say, the statistic was not good to make any claim, was not good to make any conclusion. And even, for instance, this is a measurement made by AMS-01 in the demonstration flight of 10 days in the shuttle. And the measurement also reached 30 GeV. And you see the data is more or less in agreement with the previous data. But what is also curious is that the background estimation is different. So in some sense, it was difficult on that time to see already whether it was a signal or not. By the way, both papers refer to the same code for the background estimation. So the main difference is 2004 and this is 2007. So in conclusion, to make a precision measurement of antiparticles has to be done through experiments operating outside the atmosphere in order to remove the background from the atmosphere. You need to have a long time because the rate is very small, and then you have to be running during a long time. And also you need a quite good detector capability to identify the positrons and the protons that are several orders of magnitudes. The main background is protons, and you can already mimic positrons. So in the last 10 years, 3 experiments were running. Pamela is a satellite that was launched in June 2006. Fermi was launched 2 years later, and AMS-02 that was launched in May 2011. So let me go through these experiments. Pamela is a particle physics experiment. We use particle physics detectors. The core of the detector is a permanent magnet equipped with silicon tracking for the measurement of the bending of the particles to identify the charge. A calorimeter at the bottom of the detector provides the measurement of the electrons and the positrons, and also a neutron detector provides an extra reaction power for the protons. The detector was installed on a satellite, so couldn't be very big. It's 1.3 meters, not too big. And the acceptance is not very big either. So it was launched in June 15 from Russia. And Pamela was the first experiment that provided a clear signal of really a deviation of the positron fraction with respect to the background in 2009, was published in Nature. So they measured the positron fraction till 100 GeV, and later on they provide also the measurement of the flux of the electrons and the positrons separately. So even Pamela was an experiment in the space. The experiments have a dead time and was already designed to be running during 3 years. But even now, after 8 years, they are still getting data and providing very valuable results. The second one, Fermi, was launched from KSC in the States. Fermi is a detector the design, the goal of the detector is to detect photons. So the skin of the detector is just to have a photo conversion and calorimeter at the bottom to measure measuring the E plus E minus energy. You can get the energy of the photons. 16 blocks, very huge field of view, so very big acceptance, and was launched in 2008. So even the goal of the experiment is to make gamma ray astronomy. This is the catalog for sources above 10 GeV from Fermi. The detector is quite good to measure electrons because, in fact, you measure calorimetric energy. And they provide a measurement of the E plus E minus flux. And Fermi has not a magnet to distinguish positive and negative charge. So the thing that they did was using the magnetic field, the Earth magnetic field, they focused the detector in different orientations in order to provide a separate measurement of the electrons and positrons, and therefore the positron fraction. These are the measurements from Fermi that in some sense confirm the deviation that Pamela was on, and they were measuring till 200 GeV. The third experiment is AMS-02. AMS-02 had a prototype in 1998 that was flown during 10 days on a shuttle. It was a mission that was visiting Mir, the Mir, to give some duties there, and then was 10 days flying around the Earth to demonstrate the capability of the detector to work in the environment. So it was not till 2011 that the detector was already launched from KSC. And the skin of the detector is also a permanent magnet equipped with 7 silicon tracker layers that provide the charge of the particle, and also have some specific detectors that provide better proton-electron identification and also a very good electromagnetic calorimeter to measure the energy of the electrons and the positrons. This detector is huge, it's 5 meters high, and the acceptance is several orders of magnitude bigger than Pamela. So the loading of the detector on the International Space Station was 3 days later of the launch, and since then the detector is working and providing data. This is a picture of the detector before going to the States for the launch. It was already assembled at CERN, and there is the view of the outside view of the magnet and the Vito-counters, TRD, RICH, and the ICA. AMS is an international collaboration, a huge collaboration with participating 15 countries from America, from Europe, and from Asia. There's a participation from Mexico, and has originally 600 physicists working on it. before sending the detector to the space, well, I have to say a remark that the detector was built a la particle physics. It was not a standard space experiment in the sense that you give it to the agency, to the space agency, and they provide the experiment, and then the physicists look for the results. Here was made more like any particle physics detector. So it was a collaboration. Every institute was participating in the construction of the detector and was participating in the tests that were done on ground and also on the data taking. So we went through the normal standard space qualification test for any space experiment. We went to Steek in Holland. We test the performance of the detector in the thermal vacuum chamber. And what is more important, we made 2 runs, exhaustive run for calibration of the performance of the detector at CERN. We use beams with protons, positrons, electrons, and pions running from 10 GeV to 400 GeV, and we were changing the orientation of the detector with respect to the beam in order to map really the whole detector. The purpose of the beams was already to make a zero value, a start value for the performance of the alignment of the tracker, the calibration of the time of flight, the calorimeter, the TRD, and as you can see, we were running in several beams. The data that is produced and is collected in the detector is sent through ground via the International Space Station. There is a red, they call it tracking data relay satellites that is covering, not full time, but is covering the connection. From time to time, we have slots that we cannot send the data. Then the data is stored in the detector and then reply later. It goes from the satellites to White Sand in New Mexico, and then the operation center, the control operation center is at CERN in Prevesan. So the detector is running 24 hours, 365 days, and mainly because due to the thermal conditions, in some sense, the electronics self-heat the detector. If you switch it off, the temperature goes down so quickly that you can reach the not working plateau for some of the detectors, photomultipliers, or the tracker. So we cannot switch it off. We have to be taking data continuously. These are some parameters of the station. The International Space Station is flying 400 kilometers high, an orbit of with an inclination of 51 degrees, and the orbit is covering around 90 minutes. We are taking data in all the places. The DAQ, the rate of cosmic rays runs from 300 Hertz to 2000 Hertz, so the average is around 700, and the DAQ efficiency is quite high. The loss, this 20% loss, is mainly when we go through the South Atlantic anomaly, where the magnetic field is very small and then the rate increases a lot, and the lifetime of the detector goes down very quickly. But in the rest of the areas, it's fine. So let me go a bit through the detectors. One of the important things of the AMS is that in some sense, there are detectors that are providing redundant measurements such that on fly you can self-calibrate your own stuff. The TRD is providing the separation between electrons and positrons, but also with the calorimeter we can see separation between electrons and positrons such that we can cross-check with both of them. The energy is measured by the bending of the particles in the magnet with the tracker. Also, the calorimeter is measuring the energy. And we have the trigger provided by the time of flight and a specific detector for high precision measurement of the velocity to study isotopes. In some sense, practically all the detectors measure independently the energy and the charge of the particles, such that it's quite redundant and it's very good to get calibration and systematics. Let me go through this because it's important to understand how do we make the analysis. The TRD is made of 20 layers of radiator plus a layer of drift tubes. The protons are identified by DDX, while electrons are identified by the DDX plus the transition radiation. These are the distributions that we measure in the test bin for protons and for electrons. You see the enhancement due to the transition radiation. So using this PDF, these distributions, a particle that goes through the TRD that has 20 of these layers, it's possible to define what we call an estimator that is not only more than the likelihood of the multiplication of the 20 seniors that we record in the TRD. On that way, by selecting a pure sample of electrons identified with the calorimeter, we can already characterize the shape of the estimator for electrons and for protons. We go to the calorimeter, we require that the calorimeter gives a good signal as electrons, a good electromagnetic shower, and then with that sample, we characterize the electrons. We go to MIPS, and we characterize the protons. In that sense, with this estimator, you can make a cut, and depending on where do you move, you have a sample that is more enriched or less enriched in electrons, and we have more or less contamination of protons. On that way, this is the figure of merit for the proton rejection using the TRD that you see that they reach around 10 to the 3, 10 to the 4, till several hundred GeVs. Moving this cut, the efficiency, this is for a 90% efficiency identification of positrons. If you move this cut, this efficiency can change, but also the radiation power changes. Another important detector for electrons and positron identification is, of course, the tracker, that the tracker provides the charge of the particles. There are 9 layers, 7 of them inside the core of the magnet, and 2 of them are external. This is the resolution that we expect, and this is the value that we were measuring in the test bin with 400 GeV protons and 480 GeV protons. The resolution in the measurement of the position of the tracker is around 10 microns. And what is important to keep this performance is that the alignment of the trackers, the relative position of each layer is already well known. The stability in the inner part is guaranteed because we have an internal laser alignment system that gives us the relative movement of any of the layers with respect to each other, and the outer ones are calibrated and aligned with data itself. This is a plot showing which is the deviation from the mean that we have in the residuals for every layer. Layer 2 to 8 are the internal ones, and 1 and 9 are calibrated already with data. And the third main component for the electrons and positrons is the calorimeter. The calorimeter is made of fibers, 1 millimeter diameter, distributed uniformly inside lead. The deep in radiation length of the calorimeter is 17 radiation length, and the granularity, we read the signals with PMTs with a granularity of 4 times 4 millimeters, more or less, and give us a very good map of the development of the shower, both in XY as also in Z. The resolution that was measured in the test bin was very good, around 2% for energies bigger than 100 GeV, and also since we can reconstruct the shape of the shower, we can get the measurement of the direction of the particle just with the calorimeter. Using since we are reconstructing 3D shower, we can make an estimation of whether the shower is electromagnetic or hadronic. For that, we built a boosted decision tree using 19 variables describing the shape of the shower. And it's a kind of estimator like the one that was defined for the TRD. In some sense, we were tagging electrons with the TRD, and we were seeing how the BDT, the boost decision tree estimator, behaves for electrons as well for the protons. We use the same trick by fixing a cut value. You can select a sample that is more or less enriched in electrons and positrons, and this is the figure of merit for the proton rejection. This figure of merit has also in account that we have two measurements of the energy of the electrons. One is made with the calorimeter, and the other one is made with the tracker. So for the electrons, the ratio between the calorimeter energy and the measured momentum is peak to 1, while for protons is lower. So also here is another estimator that can be used to distinguish between both samples. The trigger is given by 4 layers of time of flight with a very good resolution in the determination of the charge. And as I say, there is a specific detector for high resolution measurement of the beta that is used for isotopes analysis. It's a rich imaging Cherenkov with 2 kind of radiators, aerogel that provides a very good resolution, and sodium fluoride that has less resolution but is covering more space. These are some of the range that we reconstruct with the data. So in some sense, this is, for instance, an example of the capabilities that the detector has. This is the ISS data and the measure of the tracker charge versus the top charge, and you can see how easily it is to identify all the elements that we measure in the cosmic rays. So let's go to the measurement of the electrons and positrons. The flux in cosmic rays is measured as the ratio between the observed number of events. You have to correct for trigger efficiency, exposure time, and the geometrical acceptance. In the measurements of fraction of ratios, like for instance the fraction of positrons over positrons plus electrons, all this part is mainly common. Therefore, the measurement has a smaller systematic error because it's just the error associated to the counting of the number of events that we observe. As I say, there are 3 main detectors that provide good separation between protons and electrons: the TRD, the ICAL, and the matching between the ICAL and the tracker. And this is a plot of the calorimeter estimator versus the TRD estimator for the data. High values of the ICAL estimator means electromagnetic-like shower. Low values are hadronic-like showers. If to this sample, to this plot, we add the charge of the particle, we already have a clear identification of protons, antiprotons, positrons, and electrons. So the analysis, in some sense, is easy once you have the detector calibrated and build all the tools. You just select events here, and you just count how many positrons and how many electrons do you have. Since the background of protons is so high, still you have some contamination here. Then instead of counting, the best is to make a fit. So the thing that we do is just select a slide here and perform a fit in this estimator. This is the data. This is the template that we use for positrons. This is the template that we use for protons. As you can see, there is a clear identification between protons and positrons, and we have a small charge confusion contribution in the positron part. This is the positrons in the energy range between 173 to 200 GeV. Based on this analysis, on this method, last year AMS published the first result of the positron fraction running from 0.5 to 350 GeV, and with a sample of 6.8 million of events. From those, 400,000 events were identified as positrons. The data is compared with the previous results that have a much bigger error. The shape of the distribution already shows that there is an XX, as it was already published and reported by Pamela and Fermi. And we see that already the distribution is quite smooth. There are not sharp peaks, and it's increasing with the energy, but the rate of increasing is getting flat with energy. This year, we have performed new measurements, enlarging the energy range till 500 GeV, as well as the statistic. We have 10.9 million of positron electrons events. This is the new bin, and this is compared with the measurements that we made before. So the data already has the same characteristics. The resolution is impressive. We can see where the positron fraction already start deviating from the background. And the shape of the distribution start falling down. In fact, an analysis, rough analysis of the local slopes of this distribution gives that the slope, the maximum, is at 275 GeV. Since we have an excess, the first thing that we have to do is already to see whether there is any preferred direction where this excess is coming from. We made a study of anisotropy. For that, we use the galactic coordinates, and we put the electrons and positron arrival direction in the galactic coordinates. This analysis, you cannot do it like for the positron fraction, that is a statistical analysis of it. You have to do it event by event. So then we have to make a clean sample. We make a cut in the TRD estimator, and we put all the events in this galactic coordinates. This is the map for positrons with energy bigger than 16 GeV, and this is the map for electrons for energy bigger than 16 GeV. The thing that we do is just to make the rate of both of them, and to look for the pool of the distribution, the dispersion from the averages. And that is the map of the dispersions of the average. I must say that these blue areas correspond to areas of the sky that they are not observable from the orbit of the ISS. So ISS is orbiting, and we don't have access to these places. But the rest, as you can see, is quite uniform, and the fluctuation of the observed positron ratio is compatible with isotropy. We made a quantitative study by using spherical harmonic expansion, and we provide a limit of delta less than 0.03 and 95% confidence level for energies below 350 GeV. So, if instead of measuring the fraction, you want to measure the flux, already you have to correct for all these terms. The acceptance is computed through the geometrical acceptance of the detector, the field of view that we are using, is computed from Monte Carlo, and is modified with the own data. The efficiencies of the reconstruction of the track, the reconstruction of the software, the TRD behavior, and so on, is modified to the Monte Carlo. The modifications, as you can see, they are quite small. Data Monte Carlo agrees quite well. The trigger is computed with the data itself. Apart from for the positrons and electrons, we have the trigger from the time of flight counters, also have a trigger on the calorimeter. And apart from that, we have a pre-scaled, not trigger events that are pre-scaled, but they are not satisfying any condition. With that sample, we can compute from the data itself, which is the trigger efficiency of the data. And the time of flight, we just compute second by second, which is the efficiency of the DAQ, and we take in account the geomagnetic latitude, the cutoff. So in that way, you just count events, divided by the corrections, and this is the measurement of the electrons. based on a sample of 9.23 million of events in covering an energy range between 0.5 to 700 GeV. The energy range of the electrons is higher than for the positron fraction because the background is less stringent. On the same way, we have the flux of the positrons compared with other results. And here, the energy range goes till 500 GeV. In total, there is almost 600,000 events. So this is the plot, different scales, multiplied by e to the cube of the electrons and the positrons. And we can see that already the shape of the fluxes is quite different. The flux cannot be interpreted as a power law, a unique power law. It has already kink somewhere, and more or less where the shape of the flux change is around 30 GeV. This is the distribution, the plot of the local slopes for electrons and for positrons, and you can see that both of them have different values and also change around 30 GeV. This is the quantification of the spectral index. Also, not only on the rate, you can try to see whether the electron sample by itself or the positron sample by itself are isotropic. And we make the same exercise. Instead of making the ratio between electrons and positrons, we compare with the exposure time map, and we get limits that are quite similar to for the ratio. In fact, the anisotropy is dictated by the statistic that we have on the positrons. So for the positrons, it's 3% and 95% confidence level. Another measurement that was already provided this year was the combined measurement of the flux of the electron plus positrons. In this sense, for this sample, you don't need to distinguish between charge positive and negative. Then the contamination is less. You can relax your cuts, and you can enlarge the measurement till the TeV. This is the measured flux compared with the measurements from other experiments. And this is the plot of the spectral index. It looks like a spectral index for the combined electron plus positrons is quite uniform, and in fact it can be described by a unique power law with a spectral index of 3.1 in the whole energy range. So whether this data comes from pulsars, comes from dark matter, or nobody knows, there are thousands of models to feed the data. In fact, the thing that we do in the collaboration is, instead of looking at the different models, we try to characterize the sample with what we call a minimal model. The minimal model contains a diffuse part for electrons and positrons with different spectral index, and uncommon source flux with a cutoff and a spectral index. And with this model, we can make a simultaneous fit to the positron fraction and to the electron plus positrons, and we can determine the difference between the spectral index in the electrons and positrons, the source with respect to the electrons or the positrons, as well as the relative contributions of the electron, positrons, and source, and also the energy cutoff. This is the result of the fit on the positron fraction. You can see that the fit is quite well and can run even for very low energy values. It means that in some sense the solar modulation correction that you have to do in the positrons and the electrons, while once you make the ratio, are quite diminished. This is for the electron plus positron flux. This is the data. This is the component of the diffuse part, and this is the component of the source. For the electron flux, the amount of source that we have is much smaller because the flux is higher. So, but even the precision of the data is able to see that already we have a component here for the source, for the electrons, as well as the positrons. Positrons are dominated by this term of the source. And as divertimento, but it's very useful for the point of view of understanding the background. We can make the difference between electrons and positrons that is pure diffuse flux, and we can characterize it, and we can use it to see the parameters in the propagation models. So the data, I think that's a very high quality data that can be used to already modelize all the parameterization of the propagation models, as well as any other model of pulsars or of dark matter search. The precision is very, very good, and the main limitation that we have for the increase the energy range is nature. In some sense, the flux is very small. We have to wait a lot of time. The main systematic that we have is the charge confusion, but mainly we have to wait for more data. So in summary, after more than 3 years of operating in space, all subsystems of the detector are operational with expected performance. MS02 is collecting an average of 16 billion events per year with a high efficiency. And the collaboration has delivered the first results on lepton fractions and fluxes based on the 3 years data. Current analysis is focused on the proton and helium fluxes, antiproton to proton ratio that is important to see the dark matter pulsar disentangle. Boron to carbon ratio and fluxes for the propagation models. Also, they provide the fluxes for all the charged particles, look at the isotopes, antinuclei, exotics, anything. So, in the past 100 years, the measurements of charged cosmic rays with balloons and satellites, mainly because time, because statistics, has a typical error of 30%. And this detector operating the station that you have power from the station and you don't have background from the atmosphere can provide results with an error of the percent level. So we hope that this 30 times improvement will provide some insights. And the space station has become a unique platform for precision physics measurements. So thank you very much.
Questions? We have one question. For when it is expected some results about antiprotons?
Excuse me?
For when it is expected result from
we are working on it, and I hope that by next year we will have a flux of antiprotons covering more or less the same energy range that we are covering with positrons.
More question?
So what's the latest ideas about how long you can continue to work on the space station?
It's unclear to me. According to the NASA perspectives, they made already a prolongation of the detector will stay in the station till the station is there. The station will be maintained, according to NASA, till 2028. Nevertheless, I have to say that the detector, as any other detector, has been designed with a lifetime. So the electronic has not infinite life, and we cannot be there for 20 years. I suppose that sooner or later we start having aging effects in the electronics. Right now, everything is working quite well, but we don't have any limitation to stay there taking data. The consumables that we have, that are mainly the gas for the TRD, I think that was foreseen to be for 20 years. And we don't have any special leak in the gas. The rest is electronics.
If not, let's thank the speaker again. We'll follow now with the theoretical, I will start now the closing of the conference. And the first part of the closing is the summary talks. We will start with the theoretical summary by Rogerio Rosenberg.
Creo que sí. Okay, so Silafae is coming to an end, and I'm going to present a quick and theoretical summary of the conference, if I can. But before doing that, I want to tell you how I got involved into this summary talk. And it was really a surrealistic dialogue with one of the organizers. Let's call him R. And so R, I was having coffee with R a few weeks ago in São Paulo, and R said, I'm thinking of having a summary talk at Silafae. And I said, I think this is a bad idea. And then R replied, I'm known for having bad ideas. And then said, I would like to invite you to give this summary talk. And said, this is even a worse idea. Why me? Said, because you are, said, old? Said, yes, but I wanted to put it differently. And then I said, it's an honor to accept. So this is more or less what happened. So before I start, some disclaimer, usual disclaimer of summary talk. I could not go to all talks. There were parallel talks. Some talks, and I have no time to be comprehensive. So please forgive me if I forget some things, okay? So the theory summary is this. The standard model of particle physics, we call the standard model, passed all collider tests, and it is a consistent theory up to the Planck scale. Great, we did it. The standard model of cosmology, lambda CDM, also passed all the observational tests. Great. So, universe solved. Mission accomplished, let's go home and do other things. Well, not so fast. We still have a few issues to deal with. Natural mass hierarchy, dark matter, neutrino masses, flavor, Fermi masses in general, dark energy, baryon baryogenesis, matter and antimatter asymmetry in the universe, gravity, how to include gravity in the picture, non-perturbative QCD, we don't know how to solve. And in addition, we need more precise computations, and this includes many loops. So there are many issues that we have to deal with, and I'm happy to say that all these issues have been tackled here at Silafae. So what I want to do is to go over this, if I can. So first, I start with naturalness hierarchy. So why is the electroweak scale much smaller than M Planck? I don't know if you know this, but the Colombians realized that this is one of the most important problems. And in fact, they built a new institute to study just the hierarchy problem, the HP Institute. Did you see that? So they decided to work on this. Very good. So we think that, some research done here, so we think that there's some symmetry protecting the electroweak scale, and this could be SUSY, could be a shift symmetry, the Higgs is a pseudo-Nambu-Gaussian boson, could be a scale symmetry, or the warping of extra dimensions. So I want to talk a little bit about these two possibilities, because they were discussed here. So SUSY is a well-motivated theory, but after the LHC, the first run of the LHC, SUSY, some of the SUSY particle masses are larger than 1 TeV scale. This is the lower limit. So in my opinion, it's starting to lose some connection with the electroweak scale. And John Ellis had some mottos that he put in his talk. One of these mottos was, SUSY anywhere is better than nowhere. And also, find me a better hole. That's another motto that he found. Well, I have just one comment to say about this. Careful with what you wish for. This is a better hole, no? It could be. So Alberto gave a very nice talk, and he showed that the constrained minimal supersymmetric model is fine-tuned, but there are ways to get around this, and the light Higgs Zeno is a robust prediction of this constrained minimal supersymmetric model. And there were some talks at this conference, Pauling about precision automated calculations in SUSY, Cabrera as neutrino signatures at the LHC, and Briceno CP violation top power productions in complex minimum flavor violation MSSM. So if I can, I will put some talks that were related to these topics. So the other way to protect the mass of the Higgs boson is to have the Higgs as a pseudo-Nambu-Gaussian boson. And this is, for me, this is kind of a historical irony. So why for me this is a kind of historical irony? Because in Higgs' original paper, he wanted to exorcise the Goldstone boson. And now he is a Goldstone boson. So that's kind of an irony. Anyways, the Higgs as a pseudo-number Goldstone boson has mass protected because it's a number Goldstone boson. And it arises at a spontaneous symmetry breaking of a global symmetry scale F. And of course has no potential to start with, so the Higgs potential has to be generated at loop level. And you can usually you parameterize this as an effective theory like pions in QCD, and this is kind of already fine-tuned. So this is the electroweak scale, this is the scale of the symmetry breaking of this higher energy scale F. So there are some questions that are unanswered, like what is the UV completion of this type of model? So if the Higgs is a composite, what is the Higgs made of? If there are new resonances, top partners, anomalous couplings, and there's some work here, like Guerro talked about anomalous gauge boson vertices, Cárcamo talked about effects of resonances in Higgs to gamma-gamma, and Alberto about anomalous top quark couplings. So this is all in the context of some effective Lagrangian. We can also use the Higgs as a portal to new physics. This was emphasized by Christophe. So we can have the Higgs as a target, so observing as many channels as possible, check the coupling structure, interpret deviations of the Higgs coupling as a sign of new physics. And I like the sentence that Alberto Casas used today, that the new physics is hidden in the error bars. So this is really true. And so this is actually looking at new physics in the error bars. You can also use the Higgs as a tool, as a portal to new physics. You study, for instance, flavor-violating Higgs decays, like that, or study other objects that can decay into Higgs, like a heavy Higgs decay into double Higgs. Dark matter is a solid beyond standard model signal from the skies so far, unfortunately. So beautiful reviews by Alejandro and Matias Lopez. So there are some indirect science signals from dark matter annihilation. Alejandro told us this hint of 3.5 keV line is still controversial. Some positron excesses, Pamela Fermi, AMS. Antiprotons, antinuclei can be found also as signals of dark matter annihilation, gamma rays from dwarf galaxies, and here is a plot that Alejandro also showed on constraints on dark matter mass from analysis of dwarf galaxies, gamma rays from dwarf galaxies from Fermi-Led. And there were some works here that were presented. Verdugo just talked about this antimatter and dark matter searches in space. Nicholas, the halosphericity, extreme dark matter, and WIMP dark matter. Neutrinos. So neutrino masses and mixes requires physics beyond the standard model. Properties are described by this PM&S matrix. Almost all of the terms are known. There's a nice review by Foley, and he showed a slight preference from his fits of phase delta over pi of the order of 1.4, 1.3 to 1.4. There were many talks about neutrinos here, stereo neutrino standard model, interactions of stereo neutrinos, 3+2 neutrino models in Higgs decays, etc., etc., etc. So there are lots of activities in neutrino physics in Latin America. Flavor. So Yossi told us that there were flavor puzzles, the origins of the CKM and this lepton PM&S matrices. He showed us also the CKM rules so far. Everything is explained by CKM, plus all the experimental tests. Problems for, usually flavor is a problem for BSM model building. Scale of new physics usually very large unless there's some new physics, unless this new physics respects some symmetries like minimal flavor violation. He also told us about how to use Higgs as a tool. So we had to test the Yukawa couplings directly and also look for Higgs flavor violations. And we had some talks by Enrico on flavor from SU3, one of the symmetries, SU3 to D3 breaking, Gonzalez Canales on S3 flavor symmetry, and Vesprosvani on flavor extended spin symmetry. Dark energy. So we have some talks about dark energy. As I mentioned in one of the first slides, the standard model of cosmology plus all the observational tests. We know the equation of state of dark energy up to 5%, and it's -1 to 5%. And Gaston talked about this. We're eagerly waiting for Planck results, late December, Buscher's talk. So there are many projects that are taking data and are planned, and they will continue studying dark energy using different probes, supernovas, clusters, large-scale structure. The baryoacoustic oscillation is one of these features in large-scale structure, and gravitational lensing. So one of these projects is the Dark Energy Survey, DES, which is taking data already. The Dark Energy Spectroscopic Instrument, DESI, which is being planned. And actually, there are negotiations with Colombia, Mexico, and Brazil to enter in this DESI collaboration, and then the Large-Scale Synoptic Telescope, LSST. Actually, there is a Brazilian participation in DES since 2006. And this is a science portal which was installed at Fermilab, and this is part of the Brazilian contribution to the DES. The big challenge is how to compute the nonlinear general relativity effects in the large-scale structure. You can always do it using n-body simulations, but sometimes it's better to have, let's say, a less expensive way of doing it. And this is what Leonardo told us how to do it using effective field theory. So a technique used in field theory is being used to estimate nonlinear effects in general relativity. So there were some talks by Alex de la Macora on baryon acoustic oscillations, Beltran, scalar vector models for dark energy, Ordóñez moment transport equations. Baryogenesis, there is no satisfactory model for generation of baryon asymmetry in the universe. Usually you have V-violation from stellar interactions, but V-violation in the CKM matrix is insufficient. You need the first order electroweak phase transition and the second order in the standard model. But maybe it's possible in extensions of standard model. And there was one talk by Fong on the possibility of a model for baryogenesis he calls a cloistered baryogenesis. Gravity, I don't have much to say. The best theory we have so far for quantum gravity is string theory. And there was a talk about ADS-CFT duality in this conference. Non-perturbative QCD. So Boris talked about soft QCD processes. These are really complicated processes. Diffractive production these processes are not well understood. You need pomerons and other beasts that I don't understand what they are, unfortunately. We have talks by Albenic on non-perturbative QCD, Roja Peña, survey meson spectroscopy, and Eugene Levin on color glass condensates, and the BFKL pomeron calculus. So finally, amplitude and perturbative QCD. This is the frontline in theoretical physics. So this I took from Mastrolia talk, very nice talk. And this is very important for precise background calculations to new physics. And it has been impressive progress in the last decade. So new techniques such as generalized unitarity, cuts, recursion relations, residues, multiple integrated decompositions, etc., were developed in the last decade or so. And also very sharp automated tools were developed, like Samurai, Ninja, and then GoSum. And also a large number of tools, automated tools, were made available recently, and this is so-called next leading order revolution. So all these tools were developed, and probably you can use them. Just one of the amazing results I found in this talk by Osola is the Higgs plus 3 jets production at next leading order. That's an amazing calculation of more than 10,000 diagrams. So this is amazing. So this is important to compute the Higgs PT distribution, for instance. Very well. So this ends my talk. Now I have to give you the real summary of, so this was all warm up. Now I do the real summary of Silafae. The real summary is this. Silafae was a big success. And on behalf of the International Science Committee, I'd like to thank Marta, Diego, Rafaeli, Gabriela, Carlos Avila, Carlos Vera, Richard, Eizon, and Cesar for this excellent work. Thank you very much. This is not there are no questions in the summary talk.
Thanks again, Rogero. I thank Rafael to have a so good summary speaker. Okay. Now let's continue with the experimental summary with Carlos Sandoval.
Okay, so it's a pleasure for me to give the summary of the experimental results of the conference. We saw lots of interesting talks and results, and I will try my best to present the main results, but I apologize in advance to anyone who was not included. It doesn't mean it wasn't important or interesting, I just didn't have time. So our current experiments allow us to make precision measurements and discover new things. So I will try to summarize everything that was said in the conference. First, we saw many results from the LHC experiments. The standard model still our best theory of fundamental interactions, and the measurements from ATLAS and CMS on different cross-sections still show the predictive power of the standard model. QCD and electroweak measurements agree very well with the standard model predictions. Here we have, for example, the top quark mass measurement from ATLAS and the top quark charge asymmetry measurement, which still shows no deviation from the standard model. Obviously, apart from measuring standard model quantities, we have discovered a new particle, the Higgs boson, and we can now measure its properties. So we saw some results on the Higgs boson mass at around 125 GeV for both ATLAS and CMS. The signal strength, spin parity, and the couplings of the Higgs boson to different particles, all of which are consistent with the standard model boson hypothesis. We also looked for physics beyond the standard model. Here's a chart of all the different limits in the search for supersymmetry. In different regions, we have the inclusive searches, third generation searches, electroweak production, R parity violation. There are too many to show one by one, but just to give you an idea of all the different searches that have been done, CMS has a similar chart, of course. And here are some examples of these searches. This is the third generation summary exclusion plots from ATLAS and CMS. So there's here we have an exclusion in the LSP mass and stop mass plane. And similar for the electroweak summary exclusions, here in the LSP mass and Chargino mass planes. We also saw some searches for dark matter from ATLAS and CMS in the mono, jet, Z, W, and gamma channels. Well, so far we don't have any new physics or any hint of physics beyond the standard model. We also saw some results from ALICE, where significant progress has been made in the precision of the measurements, and the V2 mass ordering for light and strange hadrons has been measured up to PT less than 2.5 GeV. We also saw some results from the LHCb experiment. Here's the observation of the BS mu mu decay and possible observation of the B0 mu mu decay. So that's for the LHC. Then we also saw some dark matter and dark energy searches. Here are all the different direct detection experiments and the exclusion plots for spin-dependent and spin-independent cases. And we saw how the low mass region has been heavily constrained by all these experiments. We also saw some dark energy searches where we try to constrain or measure this parameter W. and we wonder if this parameter WA is different to 0. We saw two kinds of probes of this. The distance measurement based on supernova and baryon acoustic oscillations. Both give a result compatible with -1 for W. And also the second type of search is this growth of cosmic structure, where we saw the redshift-based distortions and the weak lensing. They're also both compatible with a cosmological constant, so with W equal to -1. Neutrino experiments. So we basically saw two types of experiments, the double beta decay experiments and the neutrino oscillations experiments. With the neutrino oscillations experiments, we try to understand the mass ordering, mixing, and species of neutrinos, while with the double beta decay experiments, we try to understand the identity and mass scale of the neutrinos. Oscillation experiments, we saw the T2K, Diabay, Nova, Icarus, and Opera experiments. We tried to measure theta 1,3 and establish the nature of CP violation and mass hierarchy. On the other hand, for the double beta decay experiments, we saw Gerda, Quor, Camlands, Snowplus, EXO, Next, all with different technologies. The first one is a high-resolution calorimeter, while the second one is low-resolution but large mass calorimeter, and EXO and Next are in between in terms of resolution, but all of three have potential to reach sensitivities at the level of 60 to 100 MeV. Here we try to establish the identity and mass scale of the neutrinos. We also saw some searches from space. We saw some tests of inflation from Planck. This is the 2013 Planck TT spectrum. We saw also some recent data, 2014, but not allowed to show it yet. So Planck tests the flatness, homogeneity, isotropy, entropy of the universe, and the nature of cosmological perturbations. These are the abstracts of the primordial non-Gaussianity papers. We also saw this very nice experiment, LAGO. They have an array of Cherenkov detectors in different sites at different altitudes along the Andes mountains. And the aim is to study background radiation, space weather, and high energies. And this is a very Latin American collaboration. We just saw some results from AMS. This is the electron plus positron flux. And AMS will be able to provide cosmic ray information with an accuracy 30 times better than all the other balloon and satellite experiments, which will provide new insights and allow for precision physics searches in space. We also saw some results from Moshe. We saw an suppression for energy larger than 40 eV established, composition of the cosmic rays, and some questions. Could there be changes in the hadronic interactions? Is there a fraction of protons at highest energies? Some hints of large-scale anisotropies. And here's one of the maps from the experiment. So the future, we have measured many things, and we have very nice results for in different areas. But there are still some unanswered questions, so we want to build new experiments or improve the ones we have to answer these questions. This is the Xenon NT experiment, which is the Xenon experiment after the Xenon 1 ton experiment, which will start next year. When do we expect to see something from these experiments? We don't know, but we know the timelines are a bit large, so Xenon NT will have some results here in 2020, maybe. So we're talking about 5 to 10 years for these experiments. Same is true for the dark energy experiments. We saw the DES, DESI, Euclid, LSST telescopes, where we hope to measure W0 and WA to a better accuracy, but this will probably take 10 to 15 years. Something similar happens with the neutrino experiments. We saw the Pingu atmospheric experiment, Hyper-Kamiokande, LBNE or LBNO, depending on where it's constructed. Nexton and Nexo, Super Gerda, Super Core. These are experiments that might give us some answers, but we have to wait until 2020, 2025. We expect to measure with these experiments the neutrino mass ordering, the leptonic CP violating phase, inverse hierarchy. We also saw today this very nice collaboration, the Andes collaboration, which could allow to house experiments with very that require ultra-low exposure to cosmic radiation, so we can have neutrino oscillations experiments, double beta decay experiments, dark matter detectors. Coming back to the LHC, Alice will be prepared to address the physics of the quark-Coulomb plasma phase that will arise in the upgrade, which is run 3 of the LHC. But closer to us is run 2 of the LHC. This will start next year in the spring. We are very hopeful that we will be able to find new things there. We want to measure with higher precision all the Higgs boson properties, but of course the LHC is not thought of as a precision measuring machine. It's a discovery machine. So our biggest hope is to find something new in run 2. Is there an extended Higgs sector? Can we find any signs of dark matter, supersymmetry? And we really hope we find something new. Otherwise, we could be in big trouble, like our friend here. Thank you.
Now, before the closing of the conference with words by Marta, I first want to thank you, Marta and Enrico, for teaching us to organize conference. I hope that sometime in the future I can reach the level of his conference. So now, after the naming of the local committee, I only need to agree that I thank all of them by the big effort that they did to raise funds that were necessary to support students and postdocs that come here. Finally, I also need to thank our people here, starting with Natalia from the administration, Janet, our communicator, Omar, our assistant manager, and especially the members of our group here in Medellin. So, This is a preliminary version of the photograph, and many of them are there. Our group here in Medellin have, fortunately, a lot of students, and all will be here. I don't have word to thank them because of his commitment and, sorry, and his very hard work. Especially our undergraduate students, Alejandro, Heisman is over there, Jason, Mariana, Camilo, Sergio, our master students, Camilo is over there, Dilia, Alexandra, our PhD students, Marta, David Felipe, Andres, Robinson, and Alexander, our staff, Oscar, Federico, that had the idea to have fruits in the coffee break, and Nelson, Daniel, and William Ponce. And now I give the... And now some closing words by Marta.
Okay, just very briefly, first of all, I really want to thank all of you, all of the speakers in the plenary, in the parallel sessions, all of the people that brought their posters. All of your contributions were really wonderful. I think we've had a really, really good Silafae. We've had excellent talks, and I really want to ask you all to, or a big clap for everyone that made a big effort here. We had a very special, or perhaps a rather different way of organizing things this time than the previous experiences that I've had, especially with Enrico, that we worked really well, but of course he abandoned us. In this occasion, we had really 8 universities taking part in this, and I think that speaks very well for finding ways of collaborating amongst us. Of course, in the end, when you're the local of the locals, you work much harder. And I really think that we have to especially thank Diego and his team for all of their work.
So I can't resist just adding a couple more words. So one word is that I think that all of us who've come from outside Colombia, outside the region, have really appreciated the tremendous hospitality, the friendliness, and everything that you here in Colombia have provided. So, muchas gracias. And then, if I may, I'd just like to make one little comment. So I was at a Silafae here in Colombia 14 years ago in Cartagena. And I would say that the progress that has been made by the Colombian physics community, I would say generally by the Latin American particle physics and astrophysics community since then is absolutely tremendous. Here in Colombia, there's much more participation in international projects such as the LHC. But I think one of the most encouraging developments is all the new Latin American projects pioneered by Auger, Largo, Andes, and there are many others as well. So I think that there really is a new cosmological inflation in Latin American physics activities, and I'd really like to congratulate you.